Hello and welcome to lecture series on electrodynamics. We define a vector with the magnitude and up direction, but this definition of the vector is a bit incomplete. Let's say we have a situation or a hypothesis. We have nx peers ny apples and nz bananas, and let's make a quantity, say a vector n with nxx, nyy, and nzz. So it has three components, and all three components have a different quantities, and we put them into a vector form, vector component form. So let's say we have another set of pears, bananas, and apples, and say it's m, and we say mx apples, mx pears, my apples, and mz bananas. So if we do operation like addition or subtraction, so m n plus m is equal to nx plus mx x plus ny plus my y plus nz plus mz. So they look like a vector, n and m. They add look like a vector, but what is the problem? The problem is they don't have the direction. And one more thing, if we try to transform a vector, there is a transformation law. So if we transform a vector, so in coordinate system, different coordinate system, so every component transform accordingly. But for these vectors, like we define this component form m and n, they don't follow the transformation law. Let's check this. We have a vector A. We have a coordinate system x, y, z, and we have a vector A. I can write the component of this vector. There is angle theta with y-axis, and I can write the component ay is equal to a cosine of theta, and az is equal to a sine of theta. So these are the two components of vector A, and the vector A is ax, ay, y plus az, z, and we are assuming ax is equal to 0. So Now let's rotate the the frame that we want to transform. As the coordinate frame is arbitrary, we are taking the points in arbitrary position at the arbitrary position. So we want to rotate the coordinate frame. So if I rotate the coordinate frame, so say we have again x is not rotating, x is still there. We want a new frame. This is the old frame, x, y, z, and we have new frame which is vector is still there. This is vector here, and the new frame is this is y prime, this is new frame, coordinate frame, this is z prime. So x x prime is equal to x, so it's fixed. We rotated the other two frames, so, and the angle initially was theta. Now the angle with the two frames and with the vector A is theta bar, and this angle is phi. We rotated the frame with angle phi. Now what is phi, or what is theta prime, theta bar? Theta bar will become theta minus phi, and we can write the components of the vector in new coordinate will be a cosine of theta bar, and az will become a sine of theta bar. Now we have theta bar a cosine of theta minus phi, and this will become a cosine of theta minus phi. And if we expand these relations, so ay bar will become a expansion of cosine theta minus alpha will become a cosine theta cosine phi plus a sine theta sine phi is the okay. And what these quantities are: a cosine theta is ay sine phi plus a sine theta is az sine phi. So we transform the components from one frame to other frame, and similarly for az bar a cosine of is sine of theta cosine phi minus cosine of theta sine phi, and this quantity is AZ cosine phi minus this quantity is AY sin phi. So in matrix notation we can write is y AC bar is equal to AY AC, and here we have sine of phi, sine of phi, cosine of phi minus sine. So using the transformation law, I made a mistake here. Here will be sine and here will be cosine. And here will become sin phi, and here will become minus cosine. So in matrix notation, we just transform the coordinate system and we have a transformation of components from one coordinate to other coordinate related through this matrix. So if we perform this transformation on vector m and n, and you will come up, it do not follow the transformation law. So for a vector, it is another additional constraint that it should follow the transformation law. And for more general case like rotation about an arbitrary axis, the transformation will become or xz or yx or yy or yz or zx or zy or zz. And here we have the components in the untransformed coordinate system, and we can represent all this into a compact form, and that is AI bar is equal to summation I is equal to 1 to 3 Rij A J. J is equal to 1 to 3, and I1 refer to X, I2 refer to Y, I3 refers to Z, and so on, J1 to X, J2 to Y, and J3 to Z. So if we have a second rank tensor, then we have a transformation in terms of 9 components, and 9 components can be expressed. Txx bar is equal to rxx into rxx txx plus rxy txy plus rxz txz plus rxy plus rxz plus so on. So we will have 9 such components, and more compactly we can write into double summation Tij bar is equal to summation r is equal to 1 to 3, summation r is equal to 1 to 3, and r I k r j I t k I, and all the indices are going from 1 to 3. So for more generalized case, if we have nth rank tensor, it has nth indices and 3 power n components and transformed with n factors of r. So in this hierarchy, if you check, you will find that vector is rank 1 tensor and a scalar is rank 0 tensor. So we will continue with the differential calculus in the next section. See you in next